Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples.
Hello, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams, and joining me today is Marshall Eubanks. Marshall is the Chief Scientist at Space Initiatives Incorporated. He's a former member of NASA JPL, and he has a long history of startups and work in the commercial space sector.
I also worked for the Naval Observatory. I have been in my career a radio scientist, very long baseline interferometry is I worked on that for a long time. I'm still working on it. Done Earth rotation. I mean, if I could just say a few words, what we set up first at JPL and then at the U.S. Naval Observatory was the foundation of the current navigation system. And also the infrastructure needed to, as I call it, navigate the GPS satellites. So if you use GPS, if you have a cell phone and, look up a pizza place or something you're going to go to, ultimately that's tied back to very long baseline interferometry observations of quasars. And I'm proud to say I helped set that up.
Absolutely.
And when I say tied to, I mean like literally today. Almost certainly right now, there are observations going on to sort of calibrate this whole system and keep this going. This is a continual thing. It's not just somebody did it back in the past and it's done. No, it's like a continual thing. And one of the things I hope to do is to do the same thing for the moon.
Yes. Which
is a little different, but, at a 30,000 foot level, more or less the same.
Now, most recently, you were awarded a Phase 1 development grant from NASA as part of the NASA Innovative Advanced Concepts Program for your swarming Proxima Centauri mission concept.
Yes.
Tell us a little bit about that.
Okay, well, first, we are actually in contract negotiation on that. So until you have a contract, but we expect to get that contract by next month. So then I'll feel like we've been properly awarded it. But our idea, how can we send a mission in anything like our lifetimes, our kids' lifetimes, to a star? Stars are fantastically far away. Proxima Centauri is, 4 trillion kilometers or something like that away. That's a long, long way. And it would take any of our spacecraft so far millennia to get there. Mm-hmm. So problem is it takes energy to get velocity, and you also have to, if you have a rocket, you have to carry along a reaction mass, as they call it, that you shoot out the back to send you forward. And so you're using energy to carry reaction mass that you then lose, like with the Apollo missions. The whole Saturn V was humongous 300-foot high rocket turned into a little thing that landed on the moon, a relatively little thing that landed on the moon. And where did the rest of that mass go? Well, it was both fuel and tanks for fuel and, engines for the fuel. And so it's really all about carrying fuel. And the trouble with going to stars is, it takes light 4 years to go to Proxima Centauri, 4.24. And the rocket equation tells you that rocketry is convenient when you need a velocity that's comparable to the velocity of your exhaust. So kilometers per second, no problem. 10 kilometers a second, no real problem, because you can burn things, and the exhaust from that is in the kilometers per second level. So, obviously it depends on whether you have hydrogen or methane or solid fuels or whatever you're burning, but that's how rockets work. Well, we would like to go at 60,000 kilometers a second to get to Proxima in 20 years. Why 20? Because that's a reasonable, human lifetime thing. We don't want to take 200 years. That's a cathedral, not a space mission. We want to take something like 20 years. 20 years means 60,000 kilometers a second, which means, by the way, over 1,000 times better than anything we've done so far. And we have nuclear thermal rockets, and we could maybe, with a big effort, make fusion rockets, but none of those things are, the exhaust is hot enough, fast enough to solve this problem. Now, if we had lots of antimatter lying around, we could, maybe do this with antimatter, but we don't. And we don't think antimatter is a realistic thing because you have to make it and you have to handle it. And it's very, it explodes if you touch it. So it's a hard thing. So the solution is laser beaming. You have the power sources on Earth, or maybe on the moon or in space. You have a laser, you shine it on a laser sail, and people have gone through this, and what seems like is feasible is 100 gigawatt laser. So a substantial fraction of the whole, energy, electrical production of the Earth, of the US. 100 gigawatt laser that's pushing a few square meter sail. I think the current sail design is 7 meters across. It's varied. That weighs only a few grams, 3 or 4 grams. And that's not, if you think about a pizza weighs, this pen weighs about 10 grams. So we're talking about something like this that we turn into this big sheet that's 10 meters, that's the size of the whole room I'm in here, or bigger, and then put instruments on that, put lasers on that, and all like that, and then send it to Proxima. That's tough engineering. But we think that could work. We think we could do that. So this is like pushing the envelope in sort of all directions, you might say. But we think we could do this in maybe 10 or 20 years from now. So in 10 or 20 years from now, we could launch an expedition. And what would the cost of that be? Well, space cost tends to be connected to mass. If you want to make it cheap, you got to make it light, small. So the spacecraft themselves should be relatively cheap. Now, we're not able to calculate the cost, and it might be tens of thousands of dollars even, or something like that. It might be really cheap to launch one of these. The cost is going to be in the laser. The cost is going to be in the whole laser system, which is going to be this big, huge thing that's several football fields in size, probably, that you're going to have to put like on a mountain or maybe on the moon or something, and have a nuclear power plant or something powering it. All that's going to be really expensive, but once you build it, you can launch more. So this idea is not new to us. A lot of people have had it. You don't launch one pie plate or pizza to Alpha Centauri. Launch lots, launch dozens or hundreds or even maybe 1,000. We think 1,000. The Earth rotates around the sun. You can only do this at certain times of day, certain times of year. So maybe in 1 year you could have an expedition where you launch 1,000. That's probably about the reason, the limit there. But the total mass of those things would only be a few kilograms. The total cost of them would be fairly cheap. So the question then is, well, how do you get data back? If each one is autonomous, if you're just sending 1,000 separate little mini spacecraft and they don't talk to each other and they don't share anything, your data return is going to be really limited. They were talking about, maybe a few hundred kilobits of data back from each probe. That's like a kind of thumbnail type picture. We want to do better. So we assemble these things into a fleet, a swarm. They talk to each other, and then they use all of their laser power, because each one has a laser to send back to Earth, all of their laser power together to send a coherent signal back to Earth, and thus raise the bit rate considerably. And so if you just think, well, if each one could do by itself 100 kilobytes, and yet 1,000, well, that's 100 megabytes. That's a lot better. Our goal is to send back a data return that's comparable to New Horizons. New Horizons did a good job of describing the Pluto system when it flew by. It took a year to get the data back, and we would like to get a comparable amount of data back in a comparable time, i.e., tens of gigabytes of data back in a year from the Proxima flyby. And we think with that we can do a lot of good science, take some cool pictures, get high resolution, and by high resolution I mean kilometer scale or better of the Proxima story. Not all of Proxima b, that's the planet in the habitable zone, but pieces of it, images of it. And also, if there's anything like life there, we have a good chance of detecting it. And certainly if there's anything like a technological civilization like ours, I think we have an excellent chance of detecting it.
And in fact, I remember reading your paper there about establishing communications. And yes, it's sending thousands of them, having them sort of boosting the signal. And of course, there's the attrition rate, right? Because not all.
Well, yes. I mean, again, this is something that a lot of people have had. We don't know how dangerous it is out there. We don't know how many will survive. Is it 50%, 10%? We don't really know. We'll find out, of course, but we don't know. And so this idea is not new to us, that if you send out 1,000, you have a much better chance of having some of them get through than if you send out one.
Yes. And well, I sincerely hope NASA does follow through and funds this to completion, because between the swarming Proxima Centauri concept, breakthrough Starshot, right, it's like it would be good to have multiple efforts to send probes to nearby stars. And
well, we have been working with Breakthrough Starshot. We had a contract with them. That work is now completed. The contract has been closed because it was a fixed time. But we have been working with them, and that has really, really helped us improve our work, because it's good to get criticism. It's good to hear other people's ideas. The feedback has been very, very, very important to us. So I don't regard this as really separate from Breakthrough Starshot in a sort of scientific sense. It is contractually. It's not the same proposal. It's a new proposal. BTS, Breakthrough Starshot, is not funding this at all, but we're on good terms with them, and we talked with them literally weekly, because we have a weekly meeting set up, 2 weekly meetings actually that we attend. And, so we'll see going forward.
absolutely, yes, this would be very much a collaborative sort of thing, where even if you're not working directly together, it's like you're both piggybacking off of each other's success. And
exactly,
if somebody makes it, perfect.
And one of the things that we feel very strongly is that this is a tool that will have utility all over the place in space. With 100 kilometers a second, we could get to Pluto in a year. We could get to almost anybody you might care to name that we know of in the solar system in a year or two. So you want to go to Sedna, you want to go to Eris, you want to go to Makemake, or you want to go to something closer like Triton or the moons of Uranus, say. These little pie plates could go to all of those things very quickly. And they won't tell you everything. You'll still want to have bigger missions going on. But if you want to do an initial exploration, we could do that. If you want to do an exploration of every dwarf planet, which is now dozens, I think, we could do that once we get the system developed. Same idea. Once you get it developed, the cost is in the hardware. Deploy these things and laser booster. Once you get that, we can send these things cheaply, I think, everywhere.
Yes.
And that's powerful. That'll be a national and international resource that I am sure will be used a lot. I mean, one of the things we're trying to talk to with the planetary defense at NASA is there's no reason we couldn't send a probe like this to every potentially hazardous asteroid. They're close by. Communication should be relatively easy. And, it's just like, if something's potentially hazardous, let's send a probe and see what the rotation rate is, what it looks like, all that kind of stuff.
Oh, yeah. Rapid missions. And in fact, interstellar objects, that's another potential application that you've explored extensively, haven't you?
If I was czar of this and I had a laser system and I could do 100 kilometers a second, I would for sure send something to 1I, Oumuamua, the first interstellar. And I would send something to 2I, too, Borisov, Comet Borisov, because why not? These are both interesting objects. And for centuries to come, millennia to come, they will be closer than Proxima Centauri. So as we develop the capability to get, I feel that's inevitable. As we develop the capability to get to, interstellar distances, we will send probes to these objects. Even if we find more, even if we find, if LSST or whatever finds lots more, we'll still send them to 1I and 2I, because why not? It's... And this is actually something that's frustrated me because, as you may know, I'm sure you do know, that certain astronomers and certain people have said, well, maybe 1I was an interstellar scout of some sort, or maybe a bit of interstellar trash from extraterrestrial intelligence. But if you really think that, if you're not just sort of blowing smoke, why would you want to go check it out? It would seem like that would be the thing you'd want to do. Now, that might not be worth a multi-billion-dollar New Horizons type mission with a heavy probe and so on, but I think it would be worth a pie plate.
Now, your particular proposal for doing that, for catching up with interstellar objects, that was Project Lyra?
Yes, that was. So, if you don't mind, I'll tell you a little history here. I follow and I'm active on something called the Minor Planet Mailing List, MPML. which is a mailing list for amateurs and professional astronomers who want to talk about asteroids, minor planets. And back in 2017, there was an email saying, there's this weird object and it has a high eccentricity greater than 1. Now, eccentricities can be misleading because if you don't have a lot of data on a new asteroid, if you've just been observed like 1 or 2 nights, it can easily have a really cruddy orbit and the eccentricity can be greater than 1. And eccentricity greater than 1 means it's unbound, means it's not from this solar system in theory. And so I thought, well, because this had an eccentricity of like, I think it was 3 or something. That's pretty high. And I thought, so I'll look into it, and it had a velocity at infinity. That is to say, the velocity would have, if you let it go all the way to infinity, of about 30 kilometers a second at the time. And I thought, tens of kilometers a second? No, that seemed really strange. And so I was like, hey, this should be looked at, sort of beating the drum on this, People should be observing this. And it was already past perihelion, so it's going out of the solar system. And, so one of the things we did was we looked at all the spacecraft that are out there, Pioneer, Voyager, etc. Does it go near any of them? Well, no, unfortunately it doesn't. So it's not like it's going to fly by close to Mars or something. An MRO could take a picture of it. No. It's like it's on its own path, going very much out of the ecliptic. And even at that time, if you'd had a mission that was on a rocket that was ready to go, that you could hijack, and you could have done it at the time we first observed 1I, I don't think you could have gotten to it. I don't think even New Horizons or any of those fast missions could have gotten to it. Been close for some of them, but I don't think so. But certainly by the time it's like clear that it's interstellar, which was a few weeks, no, it's already it's going away. So you're going to need to get to it. And so I started doing orbits, and I was like, to do this, even with the SLS, because at the time there was no Falcon Heavy or Starship, it was SLS. To do this with an SLS, you could maybe do it, but you're going to, for one thing, you're not going to do it this year because the SLS doesn't exist yet. And you're going to have to do a solar Oberth maneuver, which is where you go really close to the sun. So you go really fast, and then you burn your rockets there. So that's the best way to gain energy, is to do an Oberth maneuver. Go close to a massive body, so you're going fast, and then fire your rockets. And then that means you got to get close to the sun, and to do that in a reasonable time, that means you got to get to Jupiter and do a gravity assist. So you go out to Jupiter, do a gravity assist, fall into the sun, and then do this Oberth maneuver, and then get out to where you need to go. Well, right there, that tells you that's multiple years, right? Because you've got this two years or so to get out to Jupiter, and then another 2 or 3 years to fall into the sun. So that's 5 years or something like that. And Jupiter is not always in the right place. And, and then I found out that this Institute for Interstellar Studies group was working on the same thing. Celestial mechanics, of course, the same. So our orbits, we're thinking about the same. So it's like, we should work together. And we agreed to do that in like about a minute, I think, in our first conversation. Because we really were working on the same, ideas. And so we've been working together since then. Andreas Hein and Adam Hibbert, who's a really, really good celestial dynamicist, and Robert Kennedy and some other people. And we've been working since then. And basically it's still the same idea with variation. So maybe you don't go out by Jupiter, maybe but it's like you got to get this velocity. It's actually 2 velocities you got to get. You got to get this high velocity to get to it, but you also have to get out of the ecliptic plane. And those are kind of 2 separate problems. And so it takes a little bit of finagling to solve them both. And but you can do it, and you can get to it. And again, so at the time it was like, well, if we wanted to spend a heavy mission, and it's $1 billion or more. If you wanted to have an SLS or even a Starship, yeah, you could do this. You could get to 1I. It would take you a while. You're talking about 2040 probably, but you could do it. But that's $1 billion. Is it worth $1 billion? I don't know. That's a decent question. Now, I remember talking to Jim Green, who at the time was the head of the NASA Planetary Sciences Department. This is in either 2017 or 2018, saying we should do this. And he asked me a very simple question. Is it in the decadal survey? And I said, no. Jim Green said, get in the decadal survey and we can talk. And I'm like, geez. And the other thing is, like, missions are booked, manifested. it's not like you can fly a Falcon Heavy or a SLS or something like that just overnight. You got to get on the list of approved missions, and you got to get in a manifest, and all that takes years. At the same time, I was doing some ephemeris work on One Eye, and I realized we don't know where it is very well. It wasn't observed very long. And the sort of time scale we're talking about, i.e. getting there somewhere between 2040 and 2060, say, we're not going to know where it is to much better than 100,000 kilometers, a lunar distance, a light second, something like that. And it's out there in the dark. It's a small object. It's very far from the sun. It will be very dim unless you're close to it. And so I don't think a single mission could actually get to One Eye. It might be able to find it, but it would do a flyby at 100,000 kilometers, like it was, going by the moon or something. So it would not get a good picture of it. It might get a few pixels, but and this is a heavy mission. So you're going to spend $1 billion and you're going to get like 1 pixel out of it. Mm-hmm. That seems not likely to fly, literally. And so we started thinking, well, how would you find it? Well, make a whole bunch of little subprobes and then send them in advance, and then have them go by this 100,000 kilometer wide window where it might be to find out where it is exactly. But now, if you think about it, that's already close to what Breakthrough Starshot was planning on doing. So this is really where the two things kind of got together. Well, it's like, well, okay, if we're going to do that, we'll need to talk between the probes. And gee, that sounds like a swarm. And they got to talk back to Earth. And that's really where all this came from, was considering how could you get to One Eye and how could you find it before you got there. All the probes have to do is say, it's here in this 1,000-kilometer box, say. Divide it up into 1,000-kilometer boxes, put one probe in each one, and the one says, hey, it's in this one. And then you could send a heavy mission or subsequent light sail mission that's really targeted on it. It's not just flying by at 100,000 kilometer distance, but it's like flying by at 100-kilometer distance or less. So you get really good pictures, and you can find out what it really is, and so on.
Well, I'm glad you mentioned the Initiative for Interstellar Studies, because, in fact, looking back a ways, just to the whole genesis of all this, the laser sails and interstellar missions, my understanding is that this sort of began with Project Dragonfly, which was the Initiative for Interstellar Studies. That was their design study, their design competition. From there, that's where we got the ideas that went into Breakthrough Starshot, yourself and your colleagues with Project Lyra. It was interesting. It's sort of like the threads went back to this point, and then they kind of diverged. And Lyra is something that, as you said, that's something you were doing with the Initiative for Interstellar Studies, or I4IS. So would it be fair to say that after that sort of branching out of ideas, they're sort of coming back together now, where the concepts for going interstellar, rendezvousing with interstellar objects, and exploring neighboring exoplanets, that there's kind of been a convergence?
Yes. I mean, I think there has been. I mean, another thing that we've been working on together is nomadic planets.
Oh, yes.
That is to say, planets that are not connected to any star. Now, if you believe that there's about as many nomadic planets as there are stars, or there are more nomadic planets than there are stars, which is what the data we have indicates, then there should be some closer than the nearest stars. So somewhere out there in the outer Oort cloud, or maybe in the inner Oort cloud, I don't know, we don't know, but somewhere between, and if you actually run through the numbers, if you want a Jupiter-sized body, you're talking, and this is just very roughly, but we don't really know, so rough is good. You're talking about maybe one a light year away. So it's closer than Proxima Centauri, but comparable. You're talking about Earth-sized bodies, or, super Earth, sub-Neptunes, you're talking about maybe a tenth of a light year. And if you're talking about Ceres-type bodies or lunar-type bodies, probably even closer than that. The smaller the body, the quicker the microlensing is, so you have to have better and better surveys to capture what they call a cadence. How often do they take a photometric data point? And right now they're at a cadence where they can find an Earth, probably, but not a moon. But we will find these, I think, and they will be very interesting to go to. And particularly the ones that are, say, super Earth type, because if you're big enough, you could either have subsurface oceans, oceans with ice crust on them. So you're out there in vacuum, it's cold, you got a lot of ice on the surface, but underneath you have an ocean that survives by radioactive heating. Or you could have like a super Jupiter with a Jupiter with a super Earth around it that's in a sort of like Europa is, where it's heated tidally, so it's warmed up by that. Or if you actually have, I think it's about 3 to 5 Earth masses, the Stevenson planet idea, you could actually have a hydrogen atmosphere that keeps the infrared from heating enough, radioactive heating. If you had an Earth-like planet with this atmosphere, you could actually have water on the surface. It could actually be temperate. You could actually imagine a planet. It reminds me of the Ursula K. Le Guin story, the Tombs of Atlan or something like that, where you have things that have always been dark and never seen the light. And the heroine is walking around in this always dark environment. So you could literally have oceans with breakers and stuff where it's always been dark.
And yes, there has been considerable work done on how rogue planets could in fact still be carrying life forms, especially if they've got like Jovian style moons around them or Saturn like moons around them. Yeah, because those moons would still be warm in their interior because they still are orbiting their giant.
It's really interesting how looking for exolife has really kind of exploded lately. I am old enough that I actually worked on the Viking Mars mission, which was primarily a mission to find life. It did a lot of other things, including the part I worked on, but that was its core, was finding life. And when that didn't work, and whether or not it didn't work is actually debatable, but the consensus was it didn't work. When that didn't work, that whole first generation of astrobiology just was decimated. I mean, all the people I knew lost their job, had to do something else. It was as bad as Apollo, the closure of Apollo. And for a long time, looking for life was like radioactive at NASA. I mean, we've never repeated the Viking mission experiments. We've never done them better. Levin, who did the label release experiment, he always thought, we should redo this. I know how to do it a lot better. And proposed that a number of times, I don't know how many times, and it just got nowhere. It was radioactive at NASA. It's like, we're not going to touch this. But now I think it's not. And it was actually kind of refreshing, because I go to Mars meetings occasionally, and at Mars meetings for a long time, it's like, you just could not talk about Mars life. It was just like, no. Even talking about Mars fossils was kind of like, maybe, but probably not. And then I started going to ocean world meetings, which are like Europa and Enceladus and so on. And there it's sort of like, how are we going to find life on these bodies? What are we going to do? It was just so refreshing. You know, I had not heard that conversation with Mars for decades till now. This was some years ago, 5 years, 7 years ago, something like that. But for ocean worlds, yeah, and I think that's great. I think we need to do that. Because one thing we need to do is find out, well, if there is life on an ocean world, is it like us? Does it have DNA, RNA? Does it have the same genetic code? Is it different genetic code? The same set of amino acids? Different, you know, these fundamental questions, and we just don't know. So, I mean, I feel like if there's life on a nomadic planet that's out there half a light year away, we should go and explore it. Now, it's probably not going to be beachfront property. And I mean, a question I would have is, what about technological civilization and something like that? If your technological civilization starts traveling around the galaxy with generation ships, say, big habitats where people live their whole lives going from one star system to another, would you necessarily ignore nomadic planets that happen to be closer? That you could, I mean, if there was a nomadic planet with oceans and so on that you could get to in 50 years, would you ignore that for a star system that took you 500 years to get to? I have a feeling the answer to that is no. So I don't think a technological civilization would arise on a nomadic planet, but I think you might have stuff there. And so I think, you know, again, it's an extraordinary claim that would require extraordinary evidence, but there's no reason you can't consider it.
Well, yeah, in fact, I'd say half the charm of rendezvousing with an interstellar object or getting to study them up close is that we can learn about what's going on in other star systems without actually having to go there.
Yes.
Yeah. A fraction of the time and the cost, and it's a good way to maybe even figure out if there could be life in that particular system. And for
And
follow-up.
there's another sort of planetary thing that we are very familiar with, at least one planetary system, our own, which developed from a main sequence star through what you might call normal planetary formation. There are other ways to form planetary bodies or asteroids or whatever that we won't know anything about because they're, like, for example, supernova remnants sure do look to me like they might form bodies because they have all these filaments in them that look like they might be collapsing. Planetary nebula, which are the end state of stars when they throw out a lot of their gas. That gas has a lot of metals in it, astronomical metals, carbon, oxygen, whatnot. And again, there are these things called cometary knots. It sure does look to me like things are collapsing there. If you had what I call post-main sequence planets or asteroids, or alternative to a main sequence, like, say, a pulsar planet. Could pulsar planets form in situ by having an accretion disk that forms and then turns into, I don't know. But I have a feeling all of those things are possible at some level and will be then, some of them will be put out nomadically into the galaxy. And right now, we don't have any direct evidence for any of that kind of stuff. And as you know, even with exoplanets, it's like we got all these exoplanets, so we don't, hot Jupiters and stuff. So, like, who ordered that? Solar system's not like that way. Well, actually, I believe that it's fair to say that none of the exoplanetary systems we found are really a good match to the solar system. So I hesitate to say we really understand what's going on out there in terms of, like, planetary formation, body lifetime, so on and so forth, very well. We have models, we have theories, sure, and that's fine. But I have no doubt that when we start exploring these things, we'll be surprised.
Well, so if I may ask you to sort of opine here, assuming that missions to Proxima Centauri or Alpha Centauri, that these happen within our lifetime, as hoped, as anticipated, and we do get a chance to look at the exoplanets next door, in particular Proxima b, what would you hope or anticipate we might find there? Just within a modest expectation.
Well, I'm also very interested in the candidate 1 that was discovered about 4 years ago, possibly discovered. It has not been confirmed yet, but that's around Alpha Centauri A, which is the larger of the two Alpha Centauris, the binary that's Alpha Centauri itself.
Yeah.
And in fact, we're working on a paper where we talk about going to both Proxima B and candidate 1, assuming it's confirmed. I mean, obviously, if it doesn't exist, then we have to reconsider things. But now, candidate 1 would be a super Neptune, but it might have moons, and it's in the habitable zone of Alpha Centauri A. And then you have Proxima B, which is in the habitable zone of Proxima Centauri, which is an M dwarf, which is a flare star, which has very bright flares. To me, it's like comparing those two things, comparative exobiology, would be very powerful there. Like, here you have two cases you can look at that are rather different, but they actually kind of span the galactic space, you might say, of different kinds of planets. Does one have life? Do both have lives? I mean, they're actually not that far away. Do they have the same life? Is panspermia possible? There's some fundamental questions you can begin to ask that I don't know how else you would answer it, frankly. And so I think that's very, very exciting. Proxima gets to within, I think it's 8,000 AU of Alpha Centauri AB. So if you were a technological civilization on either of those systems, going to the other one would seem like almost a slam dunk. It would be much easier than us getting to Alpha Centauri. Mm-hmm. So if there is a technological civilization on one, I would expect it to be on both. Now, that's interesting because then you could say, for example, one of the troubles people have is the false positive problem, right? You say, I'm going to look for oxygen as a biosignature. I'm going to look for nighttime lights as a biosignature. I'm going to look for this. I'm going to look for that. And you go and you find it, but it's like somebody says, well, there's this chemical reaction or there's this thing here that could explain this abiologically. But if you find two systems and they have the same sort of signatures and yet they're rather different systems, there I think you have a really good case of saying, yeah, this is a real strong indicator of life, because I would expect the chemistry on these two planets to be rather different. So if you saw similar biological signatures, you would think that's probably biology. And people will argue about this for years. I mean, for decades, I'm sure. I don't doubt that at all. None of this will be accepted. I've talked to astrobiologists. None of them think that just by finding some chemical at some concentration, you're going to be able to say, yeah, there's life. Mm-hmm. They don't think that way. None of them. None of the ones I've talked to. In fact, they're not even that impressed. It's like, I remember saying, well, what if we could land on Europa and find DNA? So we've got a DNA meter, a DNA-ometer, and we land on Europa and we dig down in the ice a little bit and we find some DNA. Wouldn't you be convinced then that there's life there? It's like, well, no. For one thing, how do I know that's not contamination from Earth? But for another thing, well, maybe there's other ways to make DNA. It had to be around before life started, almost certainly. So they want more. They want like the web of life. What's the system like? What does it eat and so on? And I think we'll eventually send people there. Assuming these planets are at all habitable, I think there'll be people there. I think not in our lifetimes, maybe not even this millennium, but I think it'll happen. So we're just starting that right now.
Yeah, absolutely. There's one thing that I keep coming back to. It's the idea of how this stuff is either starting or coming together in recent years, and just how we really do seem like we're on the cusp of something extraordinary.
We can do this if we want to, right? It's just like one eye. We could go there if we want to. Now, you can argue about whether we want to spend the money or not, but the simple fact is anybody who says, oh, you can't go there, they're wrong. We could go to one eye if we wanted to. I am convinced we can go to Proxima Centauri or Alpha Centauri if we want to. And not by sending a generation ship. Obviously, you can send generation ships. You can imagine building this huge ship and it takes 10,000 years to get there. No, we could send something that gets us data back within a person's lifetime if we want to. So it's a question really, well, what do we want to do as a species?
Yeah.
And I think, yes, I think in some ways the signs are positive right now that people are interested in pushing out. And I hope it stays that way.
Well, me too. Well, Marshall, I want to thank you for coming on, and best of luck with your NIAC grant and the development of the swarming Proxima Centauri concept. I also hope to hear more about Project Lyra in the coming years. And for my listeners, keep your ear to the ground for these missions, because they promise to be very exciting, very groundbreaking, if and when they are realized. In the meantime, thank you for tuning in. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.